Scalable database design is crucial for handling the increasing volume of data and providing high performance in distributed and growing environments. Here are some fundamental principles and considerations for designing scalable databases. 1. Database sharding. Definition: sharding involves breaking a large database into smaller, more manageable parts, called shards. Each shard is an independent database that can be distributed across different servers or clusters. Considerations: choose a sharding strategy, e.g., range-based, hash-based, based on the nature of your data and access patterns. Implement a sharding key that evenly distributes data across shards to prevent hotspots. 2. Replication. Definition: replication involves creating and maintaining copies of the database to provide fault tolerance, high availability, and read scalability. Considerations: choose between synchronous and asynchronous replication based on your requirements for consistency and performance. Implement failover mechanisms to redirect traffic to a standby replica in case the primary database goes down. 3. Indexing strategies. Definition: proper indexing improves query performance by allowing the database engine to quickly locate and retrieve the necessary data. Considerations: choose indexes based on the types of queries your application performs frequently. Be mindful of the trade-off between read and write performance when creating indexes. 4. Caching. Definition: caching involves storing frequently accessed data in a cache to reduce the need to query the database. Considerations: use in-memory caches like Redis or Memcached for quick data retrieval. Implement caching strategies to handle cache expiration, invalidation, and consistency. 5. Load balancing. Definition: load balancing distributes incoming traffic across multiple database servers to ensure even resource utilization. Considerations: implement load balancers to evenly distribute read and write operations. Use algorithms that consider the health and capacity of each database node. 6. Partitioning. Definition: partitioning involves dividing large tables into smaller, more manageable pieces to improve query performance. Considerations: choose a partitioning strategy, e.g., range, list, hash, based on the access patterns and size of your tables. Monitor and adjust partition sizes to prevent uneven data distribution. 7. Vertical scaling versus horizontal scaling. Definition: vertical scaling involves adding more resources, CPU, RAM, to a single server, while horizontal scaling involves adding more servers to a system. Considerations: choose between vertical and horizontal scaling based on your application's specific needs, cost considerations, and the potential for future growth. 8. NoSQL databases. Definition: NoSQL databases, such as MongoDB, Cassandra, or Redis, provide flexibility in schema design and are well-suited for certain use cases, such as high-volume, unstructured data. Considerations: evaluate the suitability of NoSQL databases for your specific requirements, considering factors like data model, query patterns, and scalability needs. 9. Data denormalization. Definition: denormalization involves storing redundant data to reduce the need for complex joins and improve query performance. Considerations: denormalize data selectively based on read patterns and query performance requirements. Balance denormalization with the need for data consistency and update complexity. 10. Consistent hashing. Definition: consistent hashing is a technique that minimizes the reorganization of data when nodes are added or removed from a distributed system. Considerations: use consistent hashing to evenly distribute data across nodes, minimizing the impact of node additions or removals on the system. 11. Data partitioning. Definition: data partitioning involves dividing a dataset into smaller partitions to improve query performance. Considerations: choose an appropriate partitioning strategy based on query patterns and data distribution characteristics. Monitor and adjust partition sizes to maintain an optimal balance. 12. Data archiving and purging. Definition: regularly archive or purge old or unnecessary data to keep the database size manageable and improve query performance. Considerations: implement archiving and purging policies based on data retention requirements and access patterns. Consider using data tiering to move less frequently accessed data to slower, cheaper storage. 13. Backup and recovery. Considerations: implement a robust backup and recovery strategy to protect against data loss or corruption. Regularly test and validate the backup and recovery processes to ensure their effectiveness. 14. Monitoring and analytics. Considerations: implement monitoring tools to track database performance, resource utilization, and query execution times. Use analytics to identify patterns, optimize queries, and plan for future scalability. 15. Security. Considerations: implement security measures, including encryption, access controls, and audit logs, to protect sensitive data. Regularly update and patch database systems to address security vulnerabilities. Conclusion: scalable database design requires a thoughtful combination of architectural choices, data modeling strategies, and operational practices. The specific approach will depend on the nature of the application, the expected workload, and the growth patterns. Regular monitoring, testing, and adjustments are crucial for maintaining and improving the scalability of a database system over time.